The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So our next presenter is Dr. Ed Garboczi from the National Institute of Standards and Technology.
Thanks, Eric. I appreciate being here. I'm going to tell you about shape analysis. We heard some of the other speakers talk about particle shape. Flattening, elongated is the usual words we use in the concrete community. But particle shape is a three-dimensional big concept. So I'll tell you a little bit about how we can measure shape with particles. This is work that's been done over the last 14 years or so. And then putting that shape analysis into 3D models of aggregate. They say packing, but it's not the mechanical forces of concrete are not transmitted from aggregate to aggregate. They're transmitted through cement paste. So it's not exactly a packing, but I tend to say parking, but packing is good enough. I mean, you're sticking a bunch of stuff together. That's a packing. Okay, there's my collaborators. Jeff at NIST has worked a lot on this with me. Yang Liu at Boise State is a postdoc of mine. He's taking over the further development work of this model, which I'll tell you about later. And Jiwei Chen at Delft worked with me to develop the original model. The particle shape stuff, then the model. Okay, so why do we care about particle shape? I don't need to say much to this audience, but packing density, as I said before, depends on particle shape. The strength of beds of particles depends on the shape they are. Spheres kind of smush out, jagged things hold together. Rheology of fresh concrete is hugely important on the shape of particles. Early age strength is hugely important on the shape of particles, not so much later on. And then beyond the rock and sand, you have, for general particles, you have different measures of size. You have laser diffraction for sand and cement. You have sieve analysis we're all familiar with. High-speed photography, like the units that drop particles in front of a camera. And all the measures come out differently for the same particles. And they depend on particle shape. Particle shape influences particle size measurements, so particle shape you better know something about. And then a bunch of other things I mentioned there. I should mention that Jeff and I are working at NIST on a package called T-Square, where we can do more, be available to people to do more careful 3D analysis of the particles. That's under development right now. Okay, so how do I measure particle shape? So I'm thinking more of like smaller particles, sand, and it's actually easier to do it for sand and cement, things like that. You can do it for rocks too and gravel the same way. But let's talk about sand just to be definite. So we mix sand up in epoxy and make a tube of epoxy. I use some high-tech sample holders like cocktail straws. They work great. McDonald's straws work really well too for bigger particles. And so we put that in. We put it in an X-ray tomograph and scan it. So you end up with a 3D. You have slices. And you stack them all together. You have a 3D structure of lots of thousands of particles all floating around. They look like they're floating epoxy, but really they're stiff and hardened epoxy. So you have that data structure. This is the kind of CT units I use. The smaller one on the left, the larger one on the right. These are some of the slices you get. So this is the cement particles embedded in epoxy. These are two kinds of sand. The sand on the left is a little more jagged than the sand on the right, and you can see that. There's noise in there. You clean out the noise by image analysis. You don't worry about that noise. Here's blast furnace slag, smaller particle. It looks like pieces of shattered window glass, which is chemically it's pretty similar to that. See, very jagged. These are some glass beads we did. These are used in road paints to give high reflectivity as the car's headlights hit it. It bounces the light straight back. They're supposed to be spherical. You can see from that pretty clearly a lot of them are not too spherical. And so the shape of that is something that state DOTs do a lot with various tests. This was a study we did to look at the 3D shape, how close these were to spheres. And this is some industrial limestone. You can buy crushed limestone from a mine somewhere, and you can see it's Looks a lot like cement particles. And this is just for fun. NASA, it's kind of hard to get soil from the moon surface because we don't have Saturn V anymore. So they simulate a bunch of lunar soil and looking at the shape and properties of that for robotic lunar diggers, lunar excavators. So I did a study on that. And these are particles you get in plastic explosive. That's you got C4 or Semtex. That's nasty stuff. It's used a lot in industry. And those are the explosive particles, and you can get the shape analysis using these methods as well. Okay, real quick mathematics. I don't like to present mathematics, and people don't like to see mathematics, not even in math class. So in the CT analysis, you get a 3D picture of each particle. Okay, you pull it out, you take its center of mass, and they say, what's the distance from the center of mass to the surface of the particle in any directions, any latitude or longitude? Okay. If you know that, you know the particle, and you know anything about the particle. If you have a sphere, this R of theta and phi is just a constant. You said the center of a sphere, it's the same distance to every part of the particle. For random particles, like sand and gravel, it's a random function. So you just expand that with something called spherical harmonic functions. It's like 2D, people use Fourier series, cosines and sines. It's a little more complicated, but same idea. So you end up with you know what R of theta and phi is mathematically, analytically, differential, integral. So you know everything about this particle. You can do anything. You can calculate anything of the particle: moment of inertia, curvature, length, width, thickness, volume, surface area, anything you want. So now you completely know these 3D particles, these random particles, exactly, just as well if they're spheres. Now you can calculate anything you want by the particle shape. Okay. Here's some pictures where just years ago, some rocks from Wilson Quarry in California, and then you see some real digital photos, and the recreated 3D structure based on the CT and the spherical harmonic analysis, and they're very close. This is some European standard sand, their version of Ottawa sand that we use here, and again, you see the same kind of, you very faithfully recreate the shapes. You can store that all in a database of particles, thousands of particles. Okay. These are some aggregates, sand used for hot mix asphalt. You can see it's much more angular, which you tend to want for hot mix asphalt because you want it to resist form of packing that resists mechanical forces. And then you can do some quantitative things you can do. So here's a rock. It's kind of a flat rock. You can computationally define, using this database you have of the particles, its length, which is the longest distance across the rock. Then its width is the longest distance across the rock. It's also perpendicular to the length. And then the thickness, which is the longest distance across the rock, perpendicular to length and width. So it's kind of like you generate a box that just holds the particle. And so you know the dimensions of that box is kind of roughly the dimensions of that particle. For sphere, of course, L, WT would be 1. For something elongated, L would be big and WT would be small. Something flat, L and W would be big, and comparable, T would be small. So it gives you a measure, a simpler measure of the shape of the rock, or the sand grain, whatever. Okay, you can do something with that. Now you say, okay, here's in these models we talked about, here's a handful of this sand, here's a handful of this sand. Okay, they look the same. Are they different? They're different shape, but they act differently in a concrete mix to affect the rheology. Well, if you do the shape analysis, so for the European sand, do I have a laser? Yeah. So these are basically 2D sieve analysis, but not in terms of size, but in terms of shape. So this box here means L is between 1 and 2, W is between 1 and 2. If this European standard sand used in concrete or mortars, about 70-some% of the particles lie in here. It's kind of the equiax section. They're just sort of cubic or spherical. And then 22% are slightly longer. L is between 2 and 3, W is between 1 and 2. Then this hot mix asphalt sand, we only have about a third of the particles in this equiaxis box, but now the longer particles are a much higher percentage. So there your quantitative said this sand tend to be more elongated than this sand. Therefore, it should work better in asphalt than this sand, which we expect, because it's sand made for hot mix asphalt. This is sand made for mortar and concrete. Okay, so I said this work's been going on for 14 years. It's about time to standardize it. We have see, who mentioned it? Yeah, I guess Tyler mentioned the D4791 and it's used for length with the thickness of rocks. You can't really put sand particles in those calipers; it just doesn't work. So let's say we talked to this committee DO4.51. Say, could we interested in a length with thickness type test for sand? And so they were. So we're looking at trying to standardize what we're doing for sand. So in sand, it's very easy to make the samples. You have so you can test thousands of sand grains at one go. So we're making standard procedures for making the samples, suggested X-ray CT scanning procedures, not asking companies to buy a CT, but there's a lot of companies around that would love to rent out the CT to do this kind of work. And looking at standardizing automated image analysis and particle analysis procedures. That's software, the stuff I've developed. You can easily characterize the data. And then the end result will be a file, so say 5,283 sand particles, characterized geometrically in many ways, and then you probably can write into software too that to crank out lots of Excel spreadsheets of various graphs, or leave that to the user. We don't know. But that'll be I'm working on the draft standard right now. It's, as you know, if you work the standards process, it's a lot of work putting the draft standard. You can't just take a paper. You got to really think through how people can use this. But we're working on that right now. So hopefully in a couple of years we'll have a standard method for sand shape as well as for gravel shape. So let me take a couple case studies. I'll finish with that 3D packing model. So this is a study we did. My friend Mike Taylor who used to work at Granite Rock. He gave us a whole suite of, so we started with rock that was quarried, big chunks, blasted, crushed down, and then for the same source, particles of different sizes, from 20 microns up to about 40 millimeters. And so we wanted to say, does shape depend on size for this blasting, crushing process? It's pretty typical for a quarry. So we did the size analysis, the shape analysis for all different, made samples for all different sizes of particles. We end up with 58,000 plus particles. Of course, that's not one by one. That's, one sample might have several thousand in. Then we do the shape analysis, and we put in 3 size classes, about 17 microns to 0.24 millimeters, 0.24 millimeters to about 3 millimeters, 3 millimeters to 45 millimeters, just to break them up and then compare those 3 size classes. Is A is the same as B, is the same as C. It's a little easier than trying to look at the whole curve. And what we found was, and I'll show you some graphs, the particle shape parameters we use, and just an aside, particle shape parameters are a dime a dozen. There's many, many, many you can do, and they're all good or all bad. It just depends on your application. Some shape parameters do well to predict how something's going to work in your technology, your application. Some don't. So you have to kind of pick the ones that are going to work for you to help you discriminate what's good and what's bad for your application. So they're all relative. They're all equally valid and not all equally useful depending on application. So the particle shape parameters we used for this basically are unchanged. Within experimental uncertainty, they're unchanged for all 3 size classes. So I'd say in physicists, I'm a physicist, they like to say things are universal. Well, the shapes seem to be universal for a wide range of, that's a factor 3,000 in size. Okay, so those are pictures. I could have stopped there. These are pictures, all scanning electron microscopy, 11 millimeters, 2 millimeters, 0.3 millimeters. They all kind of look the same. So that's good enough for me, but we want to do a little more quantitative to publish a paper. And so we looked at this length to width ratio. It's kind of like an aspect ratio for the particles, and looked at the cumulative probability. And within uncertainty, it's pretty much the same for the small, medium, and large classes. We looked at the second aspect, because there's an equivalent box for each particle, so there's length, width, and thickness. So you can do length to width or width to thickness if they're independent aspect ratios. And again, pretty much within uncertainty. The main uncertainty was for the large rocks, because it's very tedious to do one. Those have to do one at a time, so you can't do thousands and thousands of them. You do a couple, like 100 of them. So there's a little more statistical noise in the large thing because these are larger rocks, and not as many of them are done. At the medium and small, you did thousands and thousands. Large, you did 100 or so. So that's probably why the uncertainty is bigger for that. And I'm not going to go through this parameter, but this is something more sophisticated. You can look at the curvature of the rock integrated over the whole surface, It gives you 1 over length. You can take the inverse and formulate a shape parameter, and then that tracked very closely for all 3 length classes. So again, you do sophisticated shape parameters, you do easy shape parameters. They're all kind of the same, just how useful they are for your application. Okay, and I'll do this quickly. So I mentioned that particle shape enters into particle size measurements. So any kind of particle size distribution graph you see, sieve analysis, whatever, is always the size on the x-axis, quote-unquote size, wherever that is, you have sieve opening or whatever. And then on the y-axis, you have volume fraction or mass fraction. And so the question is, what length should be used to characterize the size of the particle? In a sphere, I know what the size of a sphere is. It's diameter. If you give me a rock, what's the size of that rock? Well, this is the size of the sieve it fits through. You know, that's one size. One way it'll fit through, one way it won't fit through. You know, what's the size of the rock? What should I use to characterize the size? Can one length even characterize the size of a random particle? Probably not. But of course, some could be better than others. So what we did was I took a microfine aggregate, so something passing the 100 sieve, right? And or 200, 100, something like that. Yeah, okay. I forget. And then we did X-ray CT shape analysis, and then we computed particle size distribution with lots of different length scales and see which one was best compared to laser diffraction experiments. I think I said that. All right, so there's the laser diffraction experiments. Here's volume fraction. Here's size. These are sieve between 28 and 38 and 75 micron. They're sieved. So already the laser shows particles outside the 38 to 75 sieve analysis. So already we know sieve analysis and laser diffraction don't agree all the time. Maybe that's no surprise, but now. And then we took the same source rocks and did X-ray CT, and we graphed it versus the thickness of the rocks. And again, so it's very just to the left of all the laser rocks. The thickness is the smallest dimension on the rock, so that's not surprising. Then we did the width of the rock. Sometimes the width of the rock is used to equate to sieve analysis. And so this does agree a little better with sieve analysis. Here's the sieve analysis restrictions between 38 and 75. It agrees pretty well with sieve analysis. It's better. It's closer to laser diffraction, but not quite there yet. Then we did the length of the rock. That's the largest dimension of the rocks. These are small rocks, baby rocks, and it agrees very well with laser. So we would say that laser diffraction is sensitive to the longest dimension of the rocks more so than the medium or the smallest dimension. So, but I'm not saying they're wrong or right. They're all good particle size distributions. Just what are you going to use to characterize the particle? Okay, let me finish quickly with the A&M model. The spherical harmonics, one of the notation uses the A sub nm. That's the kind of coefficient. So we call this model A&M. So the idea is to take these real particles, these 3D representations, and pack them into a box or unit cell. You place them. They're not packing, like remember I said before. We can do either these are cement particles in water or sand and cement paste or gravel and mortar. We're not doing anything. The matrix is just empty space. We're just putting the particles in. And then once you have that geometrical model, you can use that as input into meshing models and do all kinds of fine element calculations or so. But the basic model is a geometric model. Okay. And right, so Yang Liu at Boise State is doing the development work for the version 2 is now out. We haven't made it available yet because we learned a hard lesson in this, that putting software out on the internet, you can't just say, here, take it, do what you want with it. No, people come back with questions all the time, and questions and questions and questions. So the cost and time of developing the software is equaled by the cost of supporting the software. And in this being a government institution, we're not allowed to say, oh, just do what you want with it, suck it, do what you want. We have to support it. So we haven't got the point of kind of making it public. We welcome collaborators. People, can come and say, hey, kind of copy and work with you on this. That's fine. But in terms of putting out free on the internet, we're not at that point yet because of the support issues. It was a painful lesson under my watch I learned in this. Okay, so here's some examples. I'm almost finished. So here's two mortars. Lots of fancy colors you don't see in real life, but they look cool on screen. This is a periodic boundary condition. So For small models, it's really nice to have periodic things. So a rock sticks out here, it comes back to the other side. So we basically double up the rocks. So these ones sticking out also stick in on the other side. And so the real part is inside that gray box, but the extra rocks are added to make the boundary conditions periodic. And that helps with being a small model. It helps give you better results for when you predict properties. You also can do non-periodic boundary. You basically have a box, a rigid box. You stick particles in there. These are gravel-shaped particles. And so thinking this as a concrete, so gravel particles in a mortar matrix, and they're all inside the box. And that's useful sometimes for some applications. Generally, I don't like them because these are not gigantic models with millions and billions of particles. These are models with thousands of particles. They're kind of small compared to experiment. Like this box might be, 50 millimeters on the side. That's a small piece of concrete. So periodic boundary conditions help you to get over that small thing, small aspect. Let me skip that. Okay, so try to show you that we're blending computational and material science techniques to get a very powerful way of characterizing particle shape. It could be very useful for the kind of community via the standardization process. And there's many collaborators far beyond the people on the talks. I didn't bother listening to them because it takes too long. But lots of people contribute to this, either direct work or discussions and things. And I just want to leave you with a future work, which is kind of cool. I mentioned the simulated lunar soil. Well, now we've gotten some real lunar soil. NASA will very stingily give out samples of lunar soil if you really beg and plead to make your case that you're going to do something good with it. However, they want it all back. So I have 2 grams of lunar soil that's in storage now at Jet Propulsion Laboratory in Pasadena with my collaborator, Jay Gogwin. We've got it. We're going to do shape characterization. We're going to make up epoxy samples and give all the epoxy samples back to NASA. So I'm making the samples. If I sneeze, I'm dead. Some people with dark shades will knock on my door and say, where's that stuff? But we're going to do shape characterization and then light scattering computation because people look at the way the sunlight scatters off the moon to tell us something about the lunar surface and the Martian surface. So we're going to be having light scattering computations on these real pieces of soil. Should be able to help the astrophysicists and astronomers do with this. And when I get the samples, the first thing I'm going to do is I'm going to put them down on the ground. I'm going to say, that's one small step for Ed. Hey, I was 11 years old when that happened. My parents let me stay up to midnight to watch that. I was a Apollo bug back then. So, yeah, I thought this was a little cool thing at the end. So, I'm done. Any questions? Probably over time.